Hello everyone, we are from Soft Matter Biophysics Lab, ISR Mohali, and we are going to present you our work on membrane fluctuation analysis.
In this video, we'll show you our membrane fluctuation analysis website for GOVs. We'll go from theory to practical parameter extraction and see how to estimate membrane bending rigidity from fluctuation data.
5 practical modules: theory background, angular autocorrelation visualization, Legendre mode spectrum, kappa extraction using chi-square fitting, and a full computational workflow that shows each calculation step. The core idea is simple: control fluctuations encode membrane mechanics, and we decode those fluctuations using spherical harmonics and Legendre decompositions. So let's go to the theory workflow. The theoretical foundation is Helfrich elasticity. Fluctuations are expanded in spherical harmonic modes, and thermal equipartition gives mode amplitudes. Then we complete angular autocorrelation gamma from contours and project it into Legendre modes. Finally, we fit theory to measured BAL values and recover kappa and effective tension sigma. Modes start from L equal to 2 for physical deformations. L is equal to 0 and L is equal to 1 are not safe fluctuations we want to fit. Now let's go to the interface of autocorrelation. Here we can interactively control mode selection, kappa and sigma. When we lower down kappa, the membrane becomes softer and fluctuations increase. When we keep only lower modes such as L is equal to 2 or 3, the correlation curve becomes smoother and dominated by large-scale shape motion. This shows how each harmonic mode contributes to the final autocorrelation profile. This can also show all spherical modes or none, or we can manually choose which spherical modes we want to show. We can turn off high modes. We can move up or down values of kappa and surface tension manually according to our need.
Moving ahead with the fourth interface of the website, where we have calculated different values of BL for the corresponding mode values. As we can see over here, from the graphical analysis that moving ahead for L equals to 8, the value of BL has significantly decreased. While correspondingly, for L equals to 8, from L equals to 3, bending rigidity has increased a lot, which indicates that the higher fluctuation modes, the bending rigidity is very more, thus there is high stiffness. And in the last option of this website, we can see that there are different calculated values for different mentioned physical parameters. Moving ahead with the fifth interface of the website, where the bending rigidity extraction is calculated, and we can see over here that we have option of selecting and unselecting different mentioned values for L, and also selecting the sample values, where if we will run chi-square minimization, we will actually get the value of finally calculated surface tension along with other mentioned physical parameters, which are very relevant for any biological membrane. If we'll move down, we can see further graphical analysis which are very relevant for biological membrane studies. Moving ahead with the fifth and final interface, which is our final step-by-step calculation and complete computational walkthrough of biological membrane, along with mentioned very important physical formulas which are relevant for extracting bending rigidity and surface tension. The core idea of this project of making website was to generate a random contour with different values of L equals to 2 up to L equals to 10, or we can increase or decrease over here by using the up and down arrow and running a full workflow. We can see over here that the step by step how we have calculated the different mentioned physical parameters and how the graph is plotted. As we can see over here that angular autocorrelation have two minimas because of L2 values, and if we will move down, we can see all of the mentioned formulas have all of the mentioned calculations which you might want to explore.
So, this website is educational and practical. This can be used for teaching, for method understanding, and for real analysis data pipelines. Thank you.